Thanks everybody for coming. My name is Daniel, my colleague is Andres, and we are going to talk about advanced search and top key queries in Cassandra. So before we begin, we would like to present ourselves. So we work in a company called Stratio, and it's a big data company that was founded in 2013 and became public in 2014. We have like 70 employees in Madrid, and we also have an office in San Francisco. And we have one of the certified Spark distributions. We are quite focused on Spark. So the contents of this talk will be, first, we are going to briefly overview the different query methods that already exist in Cassandra. Then we are going to talk about our implementation of a secondary index. And then we are going to talk about how this secondary index can actually work with Spark. So that will be the contents of the presentation. So first, to briefly overview what are we talking about, we have three main ways of querying nodes in Cassandra. So we can query by primary key, we can query by secondary index, and we can query by token ranges. The difference between the different selections is actually whether you want to be more expressive and be able to specify in more detail which type of data you want to retrieve from the database, or you want to be efficient and you will like to have more throughput. So the first obvious point is queries by primary key. So we have a consistent hashing in Cassandra. We know where to go for a specific query. So once a query arrives to a Cassandra node, it becomes the coordinator for that query, and we can define and we can identify which will be the node that is storing that data. So as in the sample, we can just issue a query, go through the partition key, then go through the clustering key, retrieve the rows that I want to strat, and then give back the results to the client. That is fine, but we need primary keys. So what happens when we want to make some queries that are not part of the primary key, or we cannot do it by themselves? Then we need to rely on secondary indexes. Secondary indexes basically allow you to create invertex index, so you can create index for columns that are not part of the primary key, and then you will go and retrieve the data. The problem that you have is that, as has been said in the keynote, once the client issues a query to the coordinator, then the coordinator needs to forward that query on all the nodes in the Cassandra ring, because you no longer know where to go for a specific part of data. Each index is stored locally in each node, so a node maintains the index for the data that is stored locally. So you need to go find the results in this node, and then you get back the results. Third, and sometimes more strange, we usually query for token range. A token range is defined as the queries that has the hash of the primary keys goes within a given range in the hashing function. This is usually used and implemented when you want to make some MapReduce jobs, whether they are done on Hadoop or Spark, and you need to go and define which are the splits. And the splits are used because, as is shown in the sample, given, for instance, a Spark installation, you have a Spark master, who's be the node that receives a client request. Then that request goes to different nodes, and instead of having a coordinator, as in Cassandra, what you do is you divide your query into the Spark workers. The Spark workers are going to be co-located within the Cassandra nodes, so you can actually exploit data locality. And data locality is achieved by means of finding out which is the split, which is the token range that you can actually query in a particular node, and then you are going to extract data based on that notion. This is especially nice for other queries when you want to explore your data, analyze different aspects of your data. The third part is that we can mix things in between. We already have some secondary indexes. We would like to make some Spark jobs, some of them, and we can mix them to extract data locally using the index. So we are going to first query the local index, then this data is going to bring back to the Spark worker, and then we can perform the MapReduce job as usually. So there are some problems and some things that we are missing for the system secondary index implementations. Actually, what we would like to have is more expressiveness. Users come and say, OK, I would like to have this particular query solved in Cassandra. And sometimes we reach a point where expressiveness is actually the problem. We would like to be able to make some range queries, like I would like to extract data between 2 given dates. I would like to do multivariable search. I would like to have an index that actually indexes different columns at the same time, so my query can use the index selecting different columns in one query. I will also like to have some filter search capabilities, like I would like to search for the hashtags inside a tweet message. I would also like to have some sorting. I would like to sort the fields, the results, once they come back from the index, so they will be easily analyzed in Spark. And we will be also interested in solving some top K queries. I would like to have the 10 most visited websites in the last hour, for instance. But there are things that we actually like from the index, and in particular is its architecture characteristics. So each node indexes its own data, as we have said before, and that gives you the ability to think as the index being a local entity and avoiding thinking about a distributed environment. So you can focus actually on implementing a quite nice index that it only needs to think about the local data. There is no interconnection between the different indexes. This is a natural extension point for Cassandra. You can already implement different indexes. There is an API for this. And you can create them once you have data ingested in the system. And this is something that allows you to, once you know that there is a new query that you didn't get during the database design, you can now fulfill the query. So after we start thinking about this and what were the problems that we have and which were the tools that we already have in Cassandra, we start thinking about why not use Lucene and integrate Lucene within Cassandra. And now I will pass the word to my colleague. So,
hello, everyone. So what do we like from Lucene? Well, it's a proven, stable, and fast indexing solution. It hosts all the query types we want, such as Boolean queries, range queries, and relevant search, etc. There are several successful distributed search products built on top of Lucene. And also we like that Lucene is a library and not an installable service, so we can embed it directly in the code. Additionally, it's an Apache project like Cassandra with a large user community. Oh, sorry. So now let's take a look at how it works. For that, we're going to use an example using tweets. Let's say we have a table containing tweets. We store the tweet ID, the timestamp, the message body, the user ID, and the username. First, we alter the table schema, adding a new column called Lucene. This column is going to be used in order to link SQL syntax with Lucene's one. Then we create the index in SQL, specifying the Stratio index class and indexing properties. We specify an index refresh of 1 minute, and we specify the default language, which will be English. We specify the date format is year, month, and day. Message body will be a tokenized text in English, and user ID and username will be untokenized text. Once we have created the index, we can start these inquiries. For instance, we're going to retrieve 10 tweets containing the word Cassandra in the message body. The Stratio Lucene syntax is very similar to that of Elasticsearch. To use your index, we target the query to the Lucene extra column. This column will be used to retrieve the scoring data back from the index when using relevance queries. As this query does not involve relevance, the query distribution is done using the standard secondary index process shown before. First, the query requesting 10 results arrives to the coordinator node. Then the coordinator searches on its own index for the 10 required rows. And imagine it only found 6 rows, matching the query. Then the coordinator asks the next node in the cluster to search for the remaining 4. If the next node finds the remaining 4, then the query is done, and we don't need to continue searching on the remaining nodes. Now imagine we would like to find the 5 best matching tweets containing the word Cassandra. As a top-K query, it will involve using relevance features. As before, the query arrives to the coordinator, and then the coordinator distributes the query to all nodes in the cluster, as we don't know in which nodes the more relevant results are. Each node searches in its own local index for its best top 5 results, and the operation can be done in parallel. All the local top 5 results are collected by the coordinator, and then the coordinator orders the results according to their scoring and returns the top 5 from the partial results. In order to be able to provide top-K query functionality, we performed some modifications in the Cassandra code base. We have extended the Cassandra secondary index API to provide a generic way to support this type of queries. This way, our changes are generic and can be used for other possible index implementations. First, we have added 2 additional methods to the Cassandra secondary index searcher, and one indicates that the query requires relevance, and the other specifies how to combine the partial results according to the query. Then 2 rapid methods have been added to the Cassandra abstract range command, and finally, some additional changes in getRange_slice method in the class storage proxy make the job possible. Previous filtering and relevance methods can be combined in a query at the same time. Also, different query clauses can be combined inside Boolean predicates, and in the sample, we request the tweets inside a certain time range and starting with an A or containing a B or with the word fast. Those results should be returned sorted by ascending time and then by descending alphabetical order in username. With respect to the implementation, we would like to highlight some internal details. Each SQL row is mapped to a Lucene document and each column to a field. The documents are sorted in Lucene in the same way as Cassandra's, using a sorting merge policy. Document ratings are committed to the Lucene index at the same time as the Cassandra's column families are flashed. And finally, the Lucene index segments merged are synchronized with Cassandra column family compactions. A feature is that our Lucene indexes are fully embedded in Cassandra, so no maintenance for the point of view of the user is needed, as compaction and flushes are automatically performed. As writing this type of syntax is quite error-prone, we have introduced a new query builder for this task. Query Builder provides a fluent API that allows you to easily build index-related queries. It has been designed to be compatible with the existing Java Query Builder of Cassandra, so it can be easily integrated in your existing programs. In this example, we compare the syntax differences between writing the query in the shell or writing it in Java code. As you can see, we offer a simple Fluent API that is compatible with the existing Query Builder. This facilitates the development of applications using this type of index. Now we are going to focus on how can we use the indexes from Spark. It's very important for us to combine our indexes with MapReduce frameworks as Hadoop or Spark. To do it, we have 2 requirements. First, queries involving indexes must be compatible with token range restrictions. These token range restrictions are used by Spark drivers to partition the data into small splits. Data partitions can be large, so Cassandra reads them using paging. So the second restriction for the index is to support paged reads. The last row key of a page becomes the starting point of the next page. So from the point of view of the index, this translates into returning results in the same order as Cassandra does, starting from a particular key. To satisfy the requirement, we need to store the row token and the clustering key. Since our indexes are very expressive, its integration with Spark allows Spark jobs to retrieve from Cassandra only the information that you need. It avoids the unnecessary reads produced by the usual systematic full table scan. And it greatly reduces the amount of data to be processed, speeding up the jobs. Given the internal design of Cassandra, reading n rows from an index is slower than reading the same n rows in a token range query. However, the relevance of the index stems from the efficiency to collect only the required data. Thus, we recommend taking advantage of our index if you want to process a relatively small fraction of the total data. This, as you know, is the general rule to use indexes in any case. For example, you may want to quantify only the data of a specific time range in a database that has been storing information from several years. Additionally, you may want to filter this data for a specific region. In this case, you're going to process, say, less than the 10% of the total stored data. And if we will do it in a regular full scan, imagine the wasted time reading the 90% of unwanted data. So let's put it on perspective. Here we have a graph taken from a small benchmark, and it compares the performance of Spark using a Lucene index or using full scan. We do successive queries requesting from the 1% to the 100% of the stored data. On the x-axis, we show the number of returned rows. On the y-axis, we show the query response time in seconds. We can see that the full scan time, in blue, is constant and independent of the amount of filtered data. On the other hand, we can see a high performance for the index, in orange, for the queries requesting strongly filtered data. However, the performance decays in less restrictive queries. And as the number of records returned by the query increases, we reach a point where the index becomes slower than the full scan. So the decision to use indexes in our Spark job depends on the amount of data to collect. The trade-off between both approaches depends on the particular use case. And generally, our indexes are recommended for queries retrieving up to the 25% of the stored data. Well, we're going to show a small demo. Well. Oh. Vale. Well, we have a table storing cars. And now, if I see the pointer, ¿dónde está? Ah, okay. Okay, sorry. We can see here, I'm going to maximize, I'm going to try it. Well, we can see a query requesting a certain time range, which is cars in a year, in 2013. We can see how only the cars from this time range is returned. Here we have the first query, is requesting cars, which brand starts with an F, and the second query, this one, retrieves the car whose brand name contains a Y. Another one, using Boolean queries, more complex. is this one. That is query is going to return the cars in the time range, no? From 2013, and with the brand Peugeot, Audi, or Toyota. And that's it. The dates are from the range, and the brands are the selected ones. More, we can sort results in any way. In the first query, we get the results sorted by date in ascending order and reverse order. And that's all. Your turn. No, you. Yeah. Yes.
Okay, so yep. So we are going to talk. We are going to present other tools that we have built on top of these indexes, so it may be easier for end users to use them. The first one is called Stratio, and it's an integration with Spark. It's a different integration with Spark than the one of data stacks. We started going a different path at the very beginning of this year, actually. And it provides you with a common cell abstraction for RDDs, so you can also get data from other data stores. It maintains compatibility with the system's Spark operations, and it uses the classical addition of another type of Spark context and another job config. And it's compatible with the Lucene indexes that we have presented. Next, we have a SQL layer on top of everything, on top of Spark and the Lucene indexes, that tries to unify batch and streaming queries in a single SQL-like query. So we have a common language that is SQL-like, at least it's SQL, and is compatible with the use of different data store technologies at the same time. So you can effectively make a joint query between two tables that are stored in different databases, or in the same database, even though the database may not support the join operator as Cassandra, for instance. It's based on defining different connectors, so you can define the connector you want for the database of your choice. It has this ability, and it complements each non-native supported query by the means of using Spark jobs. So the user doesn't need to think about whether it actually uses Spark or not. He just sends a SQL-like query, and it will be solved automatically. With respect to the indexes, that's what we are talking today about, we have made some small changes in the syntax so we can facilitate the creation of this type of indexes and avoid the user to write all the JSON files. So you can issue a create full text index, and you can pass the different columns that will be part of the index. This is going to be automatically processed, and the types are going to be automatically identified and matched to those of Lucene, or you can specify your own mappings. And then, for the point of view of the queries, what we have done is we have introduced a new operator in the where clause of a select statement called match. And match is used to say that whatever comes after the match is going to be interpreted as Lucene syntax. So in this case, we are trying to find all the emails that are from a particular domain, and this star@stratio.com will be interpreted as finding all emails, independently of whether a star, that belongs to a particular domain. So some conclusions: we have added new query methods. We have support for different multivariable queries with different connectors and or not. We support range queries in this type of indexes, regular expressions when you try to make full text searches, different types of full text queries like match, phrase, or fuzzy, and we support top K queries by means of adapting the coordinator logic, so we can order the results before returning them back to the user. We have made the solution compatible with the system MapReduce frameworks. So if you would like to make a Spark or Hadoop job, you can already use this solution. And we preserve the Cassandra functionality and compatibility with CQL. Both of our solutions and everything we develop is open source. We have a fork from Cassandra that contains these modifications to the Cassandra logic. And you can find them in GitHub Stratio Cassandra. Everything is published under an Apache license, so you can feel free to go take the code, modify it as you wish, and contribute. So with this, if you have any question, I'll be happy to answer now or in the coffee breaks or by email, whatever you like. Yeah.
What about Lucene? I mean, you have built on top of Cassandra the Lucene indexes, or is already in your Stratio?
What we have done is basically take the Lucene engine, the system Lucene engine, and make an integration of the Lucene indexes with Cassandra. So each time a new row.
Sorry, this is Lucene jar that you can.
Yeah, it is the system Lucene tool. Okay. So there is no modification from the Lucene part. The work is done integrating both systems. So what we have done is we link the different operations in Cassandra with Lucene. So if you define an index and you make an insert, then that insert will be passed to Lucene, so the column is indexes and everything is updated.
But anyway, you use CQL to query directly to Cassandra.
Yeah. So every CQL query that you make, your insert, for instance, the classical insert from Cassandra, will automatically go and update the existing index.
Okay,
thank you. So,
I'm just wondering if you could explain what's the use cases as to how you integrate them like this, not just use like a separate solver cloud or Elasticsearch instance for your search line queries and have separately saved.
yeah. I will say that this is highly motivated by the fact that we would like to perform some Spark jobs. So what we like to do is to, as much as possible, filter the data that we are uploading, let's say, or treating in a Spark. So the ability to use Lucene locally in each node gives you the ability to reduce the amount of data that you start moving through the cluster. That's why we choose this type of integration and not going with, let's say, external service or external integration. Yep.
How do you deal with index rebuilding?
Sorry?
How do you deal with index rebuilding in front of a schema change or something like that?
Yeah, I mean, this part is basically already supported by Cassandra. So you just connect to the existing index API, and you will be notified that this is a chain or that a compaction is going to start. So you can basically attach your operations to that different events in the system and perform accordingly.
And if you want to rebuild the index, you can simply delete index, create index, and it's rebuilt.
Yes?
How mature is the implementation? Is it deployed in production at scale?
Sorry?
How mature is the implementation? Is it deployed in production at some kind of scale?
I cannot exactly answer that, but it's going to be highly production very soon. Okay, so thank you. You have any more questions, you can find us in the coffee breaks or contact by email. Thank you.